apologies. The camera ran out of memory. So now this is a continuation of this, the first part of the video. Now we're going to discover what is tangent inverse doing over here. So here's our tangent inverse of our L. So we're going to take in lengths, we're going to spit out angles. That's what's going on here. So we're going to take in this length, and tangent inverse of 0 spits out what's going here, and that's a 0. Tangent inverse of the length root 3 over 3 is going to be what goes here, and that's pi over 6. Tangent inverse of this length 1 is equal to pi over 4. Tangent inverse of this length root 3 is equal to pi over 3. Tangent inverse of this length, positive infinity if you will, okay, that is going to be pi over 2. So we'll use this information to create a graph. Remember, that positive infinity is in quotation marks because we will never actually really evaluate the function there, or else we would be dividing by 0. But here's a set of the lengths. Here's my tangent inverse of L, okay? We'll note that it will have 2 horizontal asymptotes, one at pi over 2 and one at negative pi over 2. Okay, then we note that the function actually is going to look like this, all right, and look like this. Why is that the case? Well, let's plug our 1 here. Our negative 1 will also be here. Then notice that tangent of 0 is 0, so we put a dot right here. Tangent of root 3 over 3, which is approximately 0.57. So if this is our 1/2, this is where our root 3 over 3 will be at. This will be located at that next special angle, our pi over 6. Okay? Then at our pi over 4, we will note that later on in our pi over 4, that's where we get 1. We get 1 mapped to our pi over 4, so we go up 1 over, and that's where our pi over 4 will be at. Next we get root 3, and root 3 is approximately 1.7. So root 3 surpasses where 1 is at. This is where root 3 would be. And look, that is even higher. That's at a higher angle, pi over 4. It's at a higher angle from pi over 4, and that's where our pi over 3 is at, as you can see. And then here comes our pi over 2. Our pi over 2 is mapped to where positive infinity is at. So take a look all the way, really all the way to positive infinity. If this is stretched forever, our line gets infinitesimally close to that asymptote. So if you would want, I can actually extend this and make the asymptote go out even farther, just so you can realize that here's the line that corresponds to pi over 2. And here's where our function will go higher and higher and higher, wishing to touch the asymptote, but never touching it. As you can see, at positive infinity in length, all the way down here towards here, that's when you would pop out a pi over 2, if it was allowed, in which it's not. So this implies, this right here implies, what is the domain and range for tangent inverse? Okay, so the domain, notice, is all reals. We can plug in any real number. And so I'll create a parentheses, negative infinity to positive infinity. That's the domain. What is the range? Okay, clearly it is from negative pi over 2 to pi over 2, even though we didn't do the negatives. You can go at home and do that, and notice that you will get just the negative values over here. So this would be a negative pi over 6, this would be a negative pi over 4, this would be a negative pi over 3, and this is a negative pi over 2. You'll get those same corresponding values that you see here. Okay, and then you'll notice that the range is negative pi over 2 to pi over 2, not inclusive, because we don't include the endpoints. It never really reaches that. Okay, it never really equals positive pi over 2, and it never really equals negative pi over 2. It never outputs that value, but it does asymptotically approach it. You plug in a larger and larger number for L. You let L be a larger and larger number. Tangent inverse will approach pi over 2 in that sense. So now that we've graphed and discussed what the domain and range of tangent inverse is, why don't we do some practical problems involving tangent inverse, sine inverse, and cosine inverse, if we will. Clearing up some real estate here will allow me to do so. let me get our board nice and juicy. Okay, we'll notice, for instance, let's talk about what is sine inverse of 1/2. Okay, now we must discuss something that I've actually been glossing over, is that you can analyze the sine inverse of, or the cosine inverse, or the tangent inverse of specific values, and you may get an output that has more than one response. So let's look at what sine inverse of 1/2 is, for instance. Let's look at our unit circle. We'll notice that at pi over 6, our cosine is root 3 over 2, and our sine is at 1/2. So sine inverse of 1/2 spits out the angle pi over 6, for sure. But that is not the only time sine has a value of positive 1/2. Notice that if we go over here on this side right here, at this angle, what would that angle be? I'm not going to tell you it, but I know that it will be a negative root 3 over 2 for the cosine and a positive 1/2 for the sine. You will tell me, I know how to find that. If this is at pi, and this was raised pi over 6 over here, then this must be raised pi over 6. But since it's going clockwise, I'm going to subtract from pi a pi over 6 to discover where that angle is at. And so you know that that's 6 pi minus a pi all over 6, which reduces to 5 pi all over 6, right here. So the other value is at 5 pi all over 6. Yes, before on our tables, we were only spitting out one value. And that is not true. I could have listed 2 values, okay? The 2 values that are repeats. So here's another example, if you will. Let me clear up some real estate again. Here's another value of repeating. Inverse trait evaluation. What about the tangent inverse of 1? Well, we know at what value is tangent equal to 1. That's right. I hear you all the way from home, and you're sitting in front of your computer, or you're on your phone, or whatever device you're utilizing this to watch this. You realize that, oh hey, actually, at pi over 4, does tangent of pi over 4 equal 1? Because that's when sine and cosine have the same value. So tangent inverse of 1 should be pi over 4. But then it dawns upon you, wait a second, let's go back to that unit circle. For sure, over here at pi over 4, we have root 2 over 2 and root 2 over 2. And so their ratio will equal 1. But notice there's another location directly across in the third quadrant that will produce a similar result. Why is that? Well, this is going to be negative root 2 over 2, comma negative root 2 over 2 of the sine and cosine values. And notice that root 2 over 2 divided by root 2 over 2 is equal to 1, but similarly, negative root 2 over 2 divided by negative root 2 over 2 is also 1. And at what angle is this at? Because we're going to have to put a comma and put that angle there, because tangent inverse now has 2 values. It spits out 2 values. So notice that it is 180 degrees away from it, meaning a pi away from it. So all you got to do is add pi to pi over 4. So that's 4 pi plus pi all of 4. That's 5 pi all of 4. So notice the tangent inverse for 1 has 2 different values. Now I know what you're thinking. Well, Why didn't you do this when we were plotting the original tangent inverse? Well, notice that we restricted the range. The range of tangent inverse was from negative pi over 2 to pi over 2. We restricted the range for this very purpose. Because if we exceeded pi over 2, which this does, 5 pi over 4 has exceeded just pi over 2. And as a matter of fact, it has exceeded pi. Notice that once you do that, that you will have repeated values for your tangent inverse. And this would cause you to no longer have a function. When one input provides you with more than one output. When one input provides you with more than one output, you no longer have a function. That is exactly how the vertical line test will fail. So that's why we restrict the range of tangent inverse. But when we evaluate it, we still know that tangent inverse of 1 can equal 5 pi over 4, and tangent inverse of 1 can still equal pi over 4. But we know that if we were to consider tangent inverse as a function, we must restrict the range. Okay? So, here's another example. Let's take what is the cosine inverse of root 3 over 2? Well, all we got to do is go to our unit circle, figure out at what angle would this happen. Well, I know if my angle is pi over 6, that I will have root 3 over 2, comma 1/2 as my cosine and sine values. So this means this is equal to pi over 6. The comma's there because we're not done. Notice there's another location. Not necessarily here, not in the second quadrant because cosine is negative. Not in the third quadrant because cosine is negative. But notice in the fourth quadrant, although sine is negative, cosine is positive. And over here at this angle, we won't say what it is, but we'll just denote that cosine would be root 3 over 2 and sine would be the negative 1/2. What angle is that? You at home could easily tell me that if this whole rotation is 2 pi, and I pull back this same amount, pi over 6, I have 2 pi minus pi over 6. I multiply top and bottom by fancy number 1 to establish a common denominator. So then I have 12 pi minus pi all over 6, which becomes 11 pi all over 6. So the next one is 11 pi all over 6. That's the next special value. Okay? So we are now able to compute the cosine inverse and sine inverse of various lengths. And it's directly related to the unit circle and the special values of the sine and cosine at those special angles. So you don't have to worry about doing this. You already worked really hard in learning the unit circle, and you already worked hard learning the special sine and cosine values at those special angles. Now it's just working in reverse, which is something I know all my students can handle.